Guys, this is Mobeen. We are talking about hemodynamics. The lecture today is the velocity of the blood flow. This is the review of the lecture. We've done the full length lecture, so let's look at it. There are some assumptions to understand the velocity of the blood flow. First of all, 1 meter is about 3.3 feet or about 40 inches. So about this much. 1 milliliter is also equal to 1 cubic centimeter. So 3 or 4 drops of water can also be seen as a cubic centimeter. Cross-sectional area is when you take a cylinder, again we are talking hemodynamics, so cross-sectional area can be taken for anything, but here in our case it is cylinders. Blood vessels are like cylinders. So you take a cylinder and you cut it on a plane, that is called the cross-sectional area. If you cut it on the normal plane, that is at 90 degrees, then the area revealed will be of a circle, right? So if I take this glass or this marker here, actually marker is easier. This marker is a cylinder, and if I cut it here, the thing that you would see is a circle. So the area of a cylinder's cross section, which is cut at a right angle, is the area of a circle, and that is A equals pi r square. And the units are, in our case, hemodynamics, centimeter square. The other differences between the velocity and the flow that we should know: velocity is the movement or speed of the blood during the unit time. Flow is the amount of blood moving during the unit time. So velocity, let's say this is an RBC and this is 1 liter of blood. If they both are moving together, their velocities is the same, but their volumes are different. So velocity and volume or flow are different. Velocity is speed or distance covered in unit time, and flow is the volume passing per unit time. Now for our discussion here, these charts are really important. They can appear in your steps. Our discussion will assume a person who is healthy has an average cardiac output, and that is 5 liter at rest per minute. 5 liter of cardiac output per minute. So let's see what happens. The formula to see the velocity is flow over cross-sectional area. What that means is that velocity is directly proportional to the flow of blood, and velocity is inversely proportional to the cross-sectional area. What that means is, if you increase the flow, then the velocity increases from a unit length and unit time. If you increase the cross-sectional area, if you increase the diameter, then the velocity reduces. So larger the blood vessel, slower the velocity; smaller the blood vessel, faster the velocity. You may have seen it. If you have a water hose and you're watering the plants, when you squeeze the mouth of the hose, the blood comes out fast. So smaller diameter, faster velocity. Now look at this chart here. What this is showing is, this chart maps to this vascular structure here. This is the aorta as it comes out of the heart. Then aorta divides into arteries and arterioles. Arteries divided into arterioles. So this is that. Then capillaries. Then capillaries merge together to make venules, and finally veins are formed. This is the structure of the tree, and that structure is represented here: aorta, arteries, capillaries, venules, and veins. Now this is the cross-section graph. Aorta's cross-section is about 2.5 centimeters. I have this is 2 centimeters here. I used this ruler and drew 2 centimeter here. The cross-sectional area of aorta is 2.5 centimeter. That means if I make aorta here, this is the cross-sectional area, it is about 2.5 centimeters. However, as we reach the capillaries, the cross-sectional area is this big. Why this big? Because we summate, we take all the capillaries together, we put them together, we wind a wire around them, and then we take them out, and that is the cross-sectional area. That is a circle for which you need to have the cross-sectional area, because the blood is going into them at the same one time. So the cross-sectional area of the capillaries is normally 3,000 centimeters square. So that is a cross-sectional area. When you convert it into diameter, it's about this big. So if all capillaries were merged together to make a blood vessel, it would be this big. Anyways, now let's see how the velocity changes. I have done a couple of calculations, one for aorta and one for the capillaries, and you can then see that the same would hold for the rest. So look at the aorta, small cross section. The cross section is 2.5 centimeter. What we did was, here is the formula, V equals Q over A. We plugged the values. 5000 milliliter is the cardiac output we decided per minute. 2.5 centimeter square is the cross-sectional area of aorta. When we do what I did was I changed the milliliter here to centimeter square because we established that 1 milliliter can also be called 1 centimeter square. 1 cubic centimeter, 3. So then I divided that here. The result was 2000 centimeter per minute. What that means is the velocity of the blood flow through the aorta is 2000 centimeters per minute. If you convert it into meters, if aorta was 20 meters long, then the blood would pass through it within 1 minute. That is how fast the blood is moving. If you convert it to seconds, you divide this whole thing by 60, it's about 33 centimeters per second. So that is what we have. We have marked here 30 centimeters per second. Now let's go to capillaries. Capillaries have, of course, the cardiac output is still the same, 5000 centimeters per minute. Capillaries cross-sectional area is 3000 centimeters square. When you divide them, it comes to be 1.6 centimeter per minute. So really slow. 1.6 centimeter is here. 1.6 centimeter per minute. So 20-meter long aorta would receive all the blood and flow it within 1 minute, and this tiny capillary would still be having blood go through it. This is how much is the difference in the speed. If you convert that to the seconds, then it is 0.027 centimeters per second. That is how slow. So it almost comes to 0. Of course, it doesn't touch 0, otherwise blood would never come out. So 30 centimeter per second drops down to almost 0 centimeter per second, then merges again and goes back up to the 30 centimeter per second. That is the velocity. Now what is the significance of this? Significance is this: we don't want the blood to stand in aorta. What would it do there? If it stands there, the tissue is going to become hypoxic. So aorta should quickly conduct the blood. However, we do want the blood to stand in the capillaries so we can do gaseous exchange, nutritional exchanges, and water exchange. So for that, we really need to move it slowly so it can easily do the exchanges. So that slowness is seen because of the large diameter of the capillaries. So that is the velocity of the blood flow. Thank you.